Hello, welcome to my assignment 3 presentation. Naive Bayes, discussed in the paper, it's a statistical approach to text classification, and it's known for being fast, simple, and mathematically reliable. This is why it's used in many real systems such as spam detection and content filtering. But with the rapid growth of internet, machine learning algorithms tend to struggle with memory limits and slow processing times. That's where something like a possible solution could be found in Hadoop, and it's not to challenge the algorithm itself, but it helps scale it across large text databases by distributing the workload instead of relying on a single machine. So the main challenge introduced in this paper is how do we keep naive Bayes efficient, but also make it scalable and smarter for real internet level data. So for our machine learning overview, machine learning is often the go-to method when we deal with classification problems. So we can let the model learn from patterns directly within the data. And there are multiple algorithms that can do classification, such as naive Bayes, k-nearest neighbors, neural networks, and support vector machines. Each one has its different strengths, but naive Bayes stands out for being lightweight and efficient, and especially with text. So in machine learning components, there's often two components, such as the training set, and it contains labeled examples that teach the model what each category looks like. And then we have the model itself, which is basically the result of that learning. It's the functions that the system builds to make predictions. And once we have that model trained, we test it using a test set, and this evaluation tells us if our classification method is effective or if it needs improvement. So as discussed in the paper, and text categorization is essentially taking an unlabeled piece of text and assigning it a category it belongs to. So for instance, in this function where A is turned into B, A is the text that we want to classify into B, which is a set of categories. And there are two general ways to do this. We have our rule base where we can write explicit classification rules, and then we have inductive learning where the model figures it out from examples. And then that's the approach we're going to be discussing in the paper. So for our Bayesian theorem, in the context of text classification, probability of H given X, where H is our hypothesis and X belongs to category, and X is the unknown sample. So naive Bayes is essentially a probability-based classifier where we can essentially take, given a document, how likely that X will belong to this category, and that's the decision naive Bayes makes. So our goal is we want to compute how likely that sample text belongs to that category, and our key takeaway from this theorem is that the text classification essentially becomes a probability comparison, where we want to choose the category of the highest probability of H given X. So just for instance, how likely that unknown sample text belongs to that category, and then that's how and then the one with the highest score will win. So that's how naive Bayes essentially assigns a label. Essentially, why is naive Bayes used in text? So it performs well on large text data sets because it's not overcomplicating the process, which leads to fast and accurate results. And then it's considered naive, and we're calling it that because it assumes that each word acts as its own independently to the final classification, even though we know the language isn't that strict. And then its classification logic, as discussed in the previous slide, we're calculating a probability for each category, and we want to pick the highest. And then this works on a supervised model, meaning it's going to learn from labeled examples, and it uses it to classify the new documents. And then we have two common types of text classification, where we can use multinomial naive Bayes, which cares about how many times words appear. And then we have Bernoulli naive Bayes, which is more of a binary process, and it checks if a word appears or not. But for this one, we're going to be using the frequency-based model, which is our multinomial naive Bayes. And that works better with text content like news or articles when we have words with higher frequencies. So naive Bayes as a probabilistic network. So a helpful way to visualize naive Bayes is a very simple Bayesian network. So at the top here in this diagram, we have C, which represents possible class labels. This can be anywhere from sports, politics, or medicine. And then you follow that below, you have our X1, X2, X3, and those each represent their own words in a document. And then during the training phase, each word learns probabilities per class. So the model essentially scans through labeled examples and builds probabilities based on how strongly each word is associated with each category. And then during classification phase, it will score each class using those word probabilities, and then the highest class with the highest score, or highest probability in this case, is selected. So really this is just asking which category makes this document most probable, and that's the one that gets assigned. So one process we can use is smart feature selection. So in text classification, we can have too many raw words, and that equals noise plus slower classification. So it can slow it down and it lowers accuracy. But traditional features selection uses fixed cutoffs top inwards. But what is the best n? It changes with every data set, so using a fixed number isn't dependable. So in the papers discussed, the solution is cleaner. Instead of picking a number, it can rank words by importance and keeps adding them until their combined weight hits a certain percentage. So that way the model kind of auto adjusts and it keeps just enough meaningful words without guessing a fixed cutoff. We're essentially keeping the strongest signals and we want to drop the rest. So it's going to keep their words until their combined importance reaches a certain percentage target. Now, improving upon naive Bayes, the issue with standard naive Bayes is that it treats each word, every word, separately. It doesn't care if two words are connected with the same meaning, but in real text, word relationships matter. For example, words like virus and vaccine usually pair together in a medical context, but when they show up together, that combination is a much stronger hint about the category than either word alone. So this paper introduces mutual information, which basically checks how often words show up together within the same class, and if two words consistently appear together in one category, we can merge them into a combined feature instead of treating them separately. So our end result is that we keep fewer features overall, but each one now carries more meaning, which improves naive Bayes without making it heavier or more complicated. So the paper tested different thresholds for merging features, which is going to be our C. So when the C was too low, there were too many merges within it, and it caused noisy features, and the accuracy dropped, which made the data more messy and reduced accuracy. But when C was too high, there was almost nothing was being merged, so there was no improvement over regular naive Bayes. But they did find that the highest F1 score technically appeared at C equals 0.3, but C at 0.4 was chosen as the best trade-off between accuracy and efficiency, because it still had strong accuracy, but it ran more efficiently, so that became the default model for all experiments. And this kind of demonstrates that like merging is helpful, but too much or too little can hurt performance. All right, so with our traditional naive Bayes versus the improved in the paper, the improved model is going to perform best on topics such as sports, politics, and medicine when those categories contain strong word pairs that can be correlated, such as policy and government or injury and player. On other hand, categories like education, show little gain and slight drop due to weak features and relationships. So merging didn't really help much and slightly reduce the overall performance of those models when working in topics such as education. And that kind of confirms that merging correlated words improves accuracies when correlations are strong. So essentially, when meaningful words have relationships that exist. And in those cases, it is consistently beating the standard naive Bayes. So our key takeaway here from the experiments is that naive Bayes doesn't need to be replaced. It just needs to be worked on to have smarter features. So with slide merging and adaptive selection, it becomes a lot more accurate without losing its speed.